So I will continue this webinar with a small presentation on one of the protocols that we developed for the Rainbow platform, to facilitate the security aspect of the platform. And specifically, I will be demonstrating, or I mean, I'll be motivating and highlighting some of the features regarding the privacy preserving aspect. And in this presentation, we will look into the configuration or on verification of a device's configuration integrity. Yeah, so starting with maybe a small motivation, maybe to add on to the intro to this webinar. So there's currently today an incredible shift towards these services, or services of services, or services comprising a multitude of services. For example, we have the 5G, and now research, of course, will continue over to 6G, and we have the new Web3, and we have an incredible rise of cloud computing, AI, and the use of the blockchain technology, and virtual reality, and augmented reality, and all of these technologies. And now in 2022, we can also see the industry is moving into metaverses that actually encompass all of these technologies as services. So we see this encapsulation of services, which requires a lot of computing power and computing resources, and also these services span through a lot of domains. So many workplaces provide some services that are used by other workplaces. So we see this building of these service function chains that span through multiple companies. And at the same time, the standards for security have also changed due to these configurable these configurable services or software. And specifically, which is of interest for the Rainbow platform, is that we see that currently the standards are pointing towards new schemes being insecure in their design, and the potential or increased potential for security misconfiguration, and similarly to vulnerable and outdated components, which pushes forward some new recommendations from the security standards that we should really harden our configurations to enable secure updates to all of these services. Because without as phrased by the OWASP website also, so without a concerted, repeatable application security configuration process, systems are at a higher risk. But yeah, they are definitely high risk. So this is like the motivation for why we want configuration integrity verification, to verify the configuration integrity of our services that are deployed either in cloud or on edge devices, or wherever they might be. The problem is, of course, that we want to remotely attest these devices, and sadly, we also know that all systems can lie. So how can we actually do this? We want to verify the software of a device that can lie. So how do we do this? Well, the solution lies in the things that we call or tend to call roots of trust. These come in different shapes and have different security properties. So as mentioned by Raphael earlier in the presentation before, we have these trusted platform modules that come also in hardware form. So they offer actually a hardware solution to reporting configurations in an authentic manner. And the important thing here is that they come in a hardware solution, which means that regardless of how the software might lie, this hardware device will not lie because it's not affected by the software. The software can't interfere with whatever the TPM is saying. So we can actually ask the TPM to say something, and the software can't lie. The hardware doesn't lie because it's on a separate bus of some technicalities. Of course, we also have different other roots of trust. So we could have a trusted execution environment that offer more of a software solution that when executed, or if we execute some code in a TEE, it will actually it could, or some of these TEEs actually just stop the computing device and run in a secure world, which cannot be interfered by normal software. So yeah, so there are different roots of trust, but for Rainbow, we mostly consider this TPM device. And yeah, as Rafael also mentioned, so these TPMs offer also the opportunity to attest, which means that they offer the possibility of providing or giving us some trustworthy information about the platform. So we could store or have some secure or trusted source on the system report something to the TPM, and then the TPM will report this back to us, and the TPM will not lie. The TPM is whatever the TPM says, we can trust. Yeah. So then, of course, begs the question: so why does it have to be privacy preserving? Well, as I mentioned also in the beginning, so these or today's end-to-end services that are also used, severely used in the metaverses and also in cloud computing and in the new dynamic network layouts, comprising different these virtual functions or service function chains. But let's just consider the metaverse as an example. So it might comprise of different. So it might offer some service, and this service is only realized by passing some traffic through a multitude of different services. And these smaller services that make up this big service for the end user might also be owned or passed through different companies. So one service might use some sub-service of a different company to provide the service. And it's of course begs the question. So for example, if one of the services is owned by Google and another by Amazon, of course these are competing companies. So they also want to ensure privacy. They don't want to reveal anything if it's not necessary, which is of course we should honor that in security. But at the same time, we also want to make sure that we can trust these devices. So while we want it to be privacy preserving, we also want some assurance. And this holds true also for any safety, security, and privacy critical application, be it so for the Rainbow platform, be it these drones or human robot collaboration or whatever it may be. Most often we want it to be privacy preserving, because an untrusted verifier or a dishonest verifier can actually benefit from sensitive information, because it can actually leak different things about the platform. It can leak maybe some vulnerable software that resides on the platform, which can later be exploited. As a small example, so there are tons of reasons why we want it to be privacy preserving. We want only to reveal so it need to know basis. So we only want to reveal that, or we only want to make sure that these devices are in the correct state, but we don't want to reveal what this state is, which is very important. So moving on, as mentioned earlier also, we in Rainbow consider the TPM. And as Rafael mentioned, the TPM offers a lot of different functionalities, but we'll just strip off all these functionalities and just consider the basic case. So basically, the TPM is like we can look at it like a programmable combination safe for our keys. So we can create keys within the TPM and create some logic for when this key can be used. And the key will only be used inside the TPM, which is of course important, because if the key ever goes outside the TPM, then of course we can't trust the key, because anybody can use. So here we have created a key K. Programming and create a use policy on this key. And this use case policy, as an example, has 3 conditions to use this key. It requires that PCR4, so PCR index 4 or PCR number 4. So recall from presentation earlier. So the PCRs are these program configuration registers that we can use to store some hash values. Now this key policy requires that PCR4 has this specific hash value, and that PCR8 has another hash value, and it also requires a signature to be provided to the TPM, and it must be verifiable under a certain public key. So this signature could also come from, if everybody here has a computer, and if you run Windows, you have Windows Hello or something, and the computer might ask you to provide a fingerprint, and this fingerprint must be signed by some specific key to unlock your computer. And this is how that is done. So it requires a signature. This could be your fingerprint, a signature over your fingerprint, or some biometrics or something. But regardless, so it requires these 3. It has these 3 requirements to unlock this key. So if I were to try to sign a message using this key, the TPM's internal logic would consult this use policy of the key K, and then we would see that it references PCR4 and 8. And then it will look into PCR4 and 8, what are the values. So here we can see that PCR4 has the correct value. So that is a check mark there. But PCR8 has a different value, so no go. And similarly, we also don't have we haven't provided any signature, so that the third criteria is also not fulfilled. So in the end, the conclusion from the TPM is no, you cannot sign. Now, to sign, we need to do some measurements, provide some measurements that actually change these. So first, we of course need to satisfy the second criteria, which is PCR8. We need to make this hash value into the correct hash value to unlock the key. And let's just say that we provide this hash value, and then the TPM will try to update it. It's PCR8, and how it does that is it does it in a non-rollback manner, which means that it takes the current value of the PCR and extends that with the new value that we push in, and it creates a hash of that. So we can't go back, and we can't write directly to the PCR. We can only extend it, which is of course important, because if we could just write C2, C1A, something that ends with C1, then of course we would satisfy it. But that doesn't include the history of the PCR, and the history is crucial because it ensures that the PCR is accountable. So let's just say we extend this value, and the TPM updates the PCR, and now it got this value. So check. Now we have fulfilled the second criteria of the policy. Now to fulfill the third criteria, we also pass in a signature. Let's just say that N here is our fingerprint. Now this is the signature over our fingerprint provided by Windows Hello. And now the TPM will say, okay, you have passed in a valid signature. So third criteria is also unlocked. So this key now, in this session that we are communicating to the TPM, it will say you are free to use K as you please. So now we pass back in our message M and are free to use K, and the TPM will output the signed message. It will not output K for us to use K. It will only sign the message for us as a service, which is important because we don't want to expose the key to some untrusted area. This is basically the gist of the privacy preserving aspect that we will look into. So how do we actually use this in a private? How do we actually use this feature as a means to provide privacy respecting attestation? Well, it's simple. We just bind the PCR value inside the TPM to the correct configuration. So in Rainbow, the orchestrator of all the services has a reference list of all the services that should be realized by a specific device. And then it will just create this policy and engrave that into the keys, into the key of the specific device. And then the device can, of course, only use its key if it's in the correct configuration. So and the important thing also is that or a good let's say a nice security property that we also get is that anyone can ask the device to sign a message. So you don't have to know what the correct configuration is to know that a device fulfills or satisfies a specific configuration. You can just ask it to sign a message. And if it's able to sign the message, then you know, or you can trust that its configuration is correct. And if not, then the configuration is, of course, not correct. And this feature is important, especially for these cloud services and metaverses, all of these things, where you have these service function chains. So in the small figure here, you can see that we have a service function chain comprising 4 subservices: subservice A, subservice B, C, and D. Now, the device numbers are not important, but let's say we have this end-to-end service that comprises these 4 services. Now, service A can just call anyone that offers service B and just ask it to sign a message. If it's able to sign a message, then then it knows that it's trusted, and then it can forward the message or request from the user to this service. And the same service B does the same approach with service C, and since it satisfies its configuration and can sign the message, it can trust this service and will let the traffic pass to this service. Now, when we reach when service C tries to communicate to a specific device that offers this for service D, it runs into a problem because it doesn't get any retrieve any signature back, and this of course could be because of some availability issues, but it's also fair to assume that service D or this specific device was not able to convince its TPM to create the signature, which means that this TPM did not find the policy to be satisfiable and just prevented this device from using this key to sign the message. And then service C can just pick another service D, that another device that offers service D, and will pass it to that device. So this is one of the network or dynamic network layouts that are possible using this approach, and you can see how it works. And the important thing is that these services could be owned by different companies, so one from Google, one from Amazon, and these services learn nothing about the other one except that they are correct, because we have this privacy preserving property. Now, of course, some challenges are, so how do we actually create this key, or how does the orchestrator remotely create this key? Because I mean, so you don't actually, so if you have an edge device, you don't pull it into your hands physically and communicate to TPM to create a key. You have to do it remotely. So how do we do this remotely? How do we create this key with some specific policy? Luckily, some of the features one of the features that TPM has is it has this command called certify creation, where the TPM actually will create a certificate which proves that this key was created by this TPM and has these properties and is bound to this policy, which allows us to reliably create keys remotely. Now, the second one is how do we actually facilitate updates to configurations? And specifically for the Rainbow platform, we are talking also about live systems. So it's not a system that has the same configuration throughout its lifetime or throughout its booted state. So its configuration might change frequently while it's live. So how do we facilitate this? And how do we actually measure the configuration of the system in a reliable manner? Because remember, as I also talked in the beginning, so these systems can lie, and only when we have measured something into the TPM, then it's safe. But the measurements outside the TPM that we actually extend into the TPM, how can we trust those? So there are different solutions. So one is to have some tracer module that does this tracing of the configuration inside some trusted OS code or in some protected memory pages that are accessible only by trusted OS code. Or the other one is to use another root of trust that we can use for measurements. For example, a trusted execution environment that has grips or some clause to the running system. Because the TPM it's a passive unit. It doesn't interact with the system. The system can only interact with the TPM. But the TEE, we can actually use that to reliable methods. And the second one, of course, regarding secure configuration updates is how do we actually enforce new policies? Because we have one key and one policy, and this key is bound to this policy. And if we change the policy, then we need to change the key or create a new key. So that is the first solution, is just to deploy a new key and then have TPM certify that key. But the problem is, of course, if we have like thousands or millions of devices or services, we have to deploy new keys very frequently. And these keys, the public key of these keys should also be distributed to all verifiers to perform the verification of the signatures, which means this is extremely unsatisfiable because it's not scalable, and it's also a time-consuming process to create keys. Luckily, the TPM also has a fix for this, which is using policy authorize, which actually allows us to create one key bound to another key that governs when or what policy it's bound to. That might sound very complicated, but it's actually very simple if you think about it. So you have a key that is.
Apparently, Heini lost his connection completely. And if this doesn't work out, I've got the slides and we'll take a look at the conclusion he planned to make. This was the last part I saw him explaining. And he was just telling us that those key-based policies apparently can be updated by replacing the key. And the other mechanism to do an update would be to use this TPM command, which allows to switch the policies between keys. Now, to give his conclusions here, the protocol he presented has the key properties here that it allows the privacy respecting.
Hello.
Heini, you're back.
How long have I been away?
I think 3 minutes or 5 minutes, something like this. So I was
Okay.
just activated the backup plan.
Okay, yeah, I just heard something. I thought just someone connected, but it might have been me that was disconnected.
Yeah. So I just completed that slide for you. And perhaps you would like to take over with your conclusions.
Sure. You finish what slide? So the discussion?
This one here, yeah. No, this one.
Okay. Okay. Yeah. 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 Sure. I can just move on to the channel and conclusions if you finish with that. So yeah. So our protocol offers these um, properties public verifiability, which is very important because, and it's something we allow because, or don't put any constraints on, because we don't reveal any details. So the
Yeah, we still have more audio problems from Heini's side.
yeah, I'm back.
Now you're
I
back
think
again.
the network here is not so good. So yeah, so for the third one, as Rafael mentioned, for using the quote operation inside the TPM, where the TPM and reports this to the verifier, and then the verifier has to decide if it should trust or not these reported measurements. This requires the verifier to have a large database and to maintain this database of trusted values. And whereas in our approach, the verifier doesn't need any knowledge about the remote system. Yeah, there's one more thing yeah, here we go. So for current work, we also have considered extending these policies with some time constraints to ensure that even if if the orchestrator has authorized some policy and now the device disconnects, it could be a malicious activity or something else, then the authorized policy will time out eventually or after some specific time, which also prevents some malicious activities where a device might try to reuse a policy and just ignore further updates. Yeah, that was basically this presentation. Thank you all for listening, and if there are any questions, just feel free to ask.
Yeah, I may have a short question.
Mhm.
So, yeah, when updating the PCR-based key policies,
Mhm.
does the TPM offer protection against so-called rollback attacks? And yeah.
Yeah. So yeah. So I guess it's a two-parter. So yeah. So when we consider PCRs, then the TPM itself offers as I mentioned. So it doesn't allow us to write them.
Okay, now I do not hear you.
Oh, okay. As we have more technical problems on that line, I suggest we postpone the questions on to Heini's talk until later. Perhaps you can reconnect.